So now that you've seen how to calculate all of the loads along the length of the shaft that we're designing, you know what the moment is everywhere, you know what the shear is everywhere, and you know what the torque is everywhere in the shaft. And those are the loads in the shaft. Those are the loads that the shaft has to be sized to support. So let's go over, I've drawn a model of the shaft in SolidWorks. I'm running it on Go Remote through a web browser. You may not have this rotate tool here. If you don't, the way you get it is by going up to the menus and going down to Tools and then say Customize. I always get confused between Options and Customize. Customize is the one we want. And then you can go to Commands, and the particular one you're looking for is in the View toolbar. It's this one right here. It's really handy. I don't know why it's not a default anymore, but you just take this and drag it and drop it right over there. And I've already done that, of course, so I've got the command right here. But it's a really handy command because now I can freely rotate. It's a fairly intuitive thing. But you can see along here, along the length of the shaft, you got to right click and get the pointer back. Oh, there we go. You can see along the length of the shaft how I've designed it to have a sled runner key, a profile key, and a sled runner key in that order for the various gears along the length of the shaft. And then I've got a couple of lands here and here for the bearings. I believe the distance between each was, it was specified in the problem. You can see several of the features that I've chosen to include. I've got some snap ring grooves on either side of the gear that rides here in the center for power input to the shaft. I've got a snap ring groove down here as well as the key here that will cause stress concentration. And we can talk about which stress concentrator should be the one used at this shoulder for the gear. That's something worth talking about. It depends on where load is in the shaft. My argument would be that the stress concentration factor for the groove feature over here is going to be 3, but really that's outside of the area of the shaft that is stressed, so I don't think we should use it. Rather, we should either use a sharp or well-rounded shoulder stress concentration factor here, or for the sled runner key seat we should use that stress concentration factor. And what I would do when I have a choice, and either one would be fairly valid or equally valid, I would choose the larger stress concentration factor for all of my calculations. So that kind of gives you an idea of what all there is. You saw the loads last time. I've actually included some diagrams. I've drawn some sketches. Let me turn them on where you can see them, and I'll try to get a normal view to them. Let's see, so if we look at it from this direction, yeah, that's fine. So if I go into this diagram, let me edit it. I've made the length of the lines proportional to the amount of torque. So this is my torque diagram along the length of the shaft. So I've got about 149 newton meters of torque on this half of the shaft, but 298 newton meters of torque on this right hand side of the shaft. So a large difference in the amount of torque on the shaft. But the torque diagram is something students often miss. Students think of the shear and moment diagram because you've been doing it for what, 2 or 3 classes now, and so they think of that, but they don't think of the torque diagram. And the torque diagram is important because the torque varies along the length of the shaft. Now the input torque at C is different than the amount of torque that flows along each section of the shaft. So just understand that the torque you calculate that goes in at C gets split up and flows 2 different ways. Of course, the 149 newton meter torque flows out to one gear, and the 298 newton meter torque flows out to the other, and both points are rotating at the same speed. So there's a different amount of power that flows out to the gears on the end. They don't receive the same amount of power. Now there's some interesting features here you can see in this view. Let me zoom in just a little bit. You'll notice that this section here, let me get my pointer back, there we go. This section where I'm going to mount a gear has a really deep snap ring groove. I didn't realize that was so deep. I don't know if you can see that on the video, but that's exaggerated. I don't intend to make the groove that deep. Anyway, you'll notice that there's a fairly sharp shoulder here, whereas here there's a fairly well-rounded shoulder. What's this for? Well, remember the bearing slips onto this section of the shaft. So as I slip the bearing's inner diameter onto this shaft, I don't want to mess with this section, right? I don't want to have any real resistance there. And this nice, well-rounded shoulder should help locate the inner diameter of the bearing on its land here, and then of course this shoulder here represented by this line will stop the bearing in its appropriate position. So there's a few features. The other half of the shaft is almost a mirror image. The sizes may be a little bit different depending on what bearings I've chosen. And understand that part of shaft design involves bearing selection as well, because you've got to decide what the inner diameter is going to be of the bearings you plan to use, and of course those bearings have to be able to take the load, whatever the load happens to be at that point. So that's another big part of the process in designing this shaft, is the interplay between the shaft diameters and the bearing. Now the shaft diameter minimums are calculated from the equations that we've got for that, and I'll show you those in just a second. But once you get the minimum diameters, then you have to have a bearing with a bore of at least that, and of course they're a standard size, so you bump it up to the size of the bearing. Alright, so there's the torque diagram. Let's shut that off. You've already seen all of the... oh, I've got to exit the sketch. You've already seen all of the loads from last time. So let's view the vertical forces. We'll look at the vertical plane first. And let's see, go into the sketch. Now you can't see it, so I'm going to right click and go normal to the sketch so that it turns around. There we go. So now you can see it. It flipped the shaft around on us, but that's okay. So what I've done is I've drawn arrows to represent the magnitude of the shear at the various points. And of course remember that these, I don't remember if these came from the radial or the tangential loads, but they come from the gear tooth loading. You could tell if you saw the horizontal forces, whichever one's bigger is going to be the tangential. And since they're all in the same direction, though, these will be radial. I've got this one marked, WRC, so it's the radial load at point C. So the vertical plane must end up being all the radial loads in this case. Understand, it would be different if you didn't have the gears across the shaft from each other, right? If you had gearing at different angular positions around the shaft, well then, you know, the WRC could be in a totally different plane. Or WR for any of these loads could be in a totally different plane. But this is the way that it came out when we performed our shear diagram, or our shear calculations. Well, actually, these are the loads. These are the forces. These aren't even the shears. Sorry, I've got the shear also. I just misspoke. So these are the loads applied at the various points. And let's exit that sketch. And I forgot I put that in, and then hide it. And then I'll show you the shear diagram. There we go. Turn that on. There you go. You can see it, and go into the shear diagram so you can see magnitudes. Now, I think what I did, if I remember correctly, is I put these in at 1/10 of what the actual load was. So if I remember right, it's 2,135 newtons of load here, not 213.5. If I went to 2,000 and some odd, and I'm actually putting dimensions here, right? If I went that far out in millimeters, it'd be way off the page. You couldn't even see the shaft. So I just scaled it down by an order of magnitude. The center line of this diagram is the center line of the shaft. And so you can see the magnitude of the shear here. There's a positive shear, still positive here, and then it flips to negative shear in the last two segments, which makes sense. That's a simple thing. So there's the shear diagram. Let me exit that and make it where we can't see it. And then the horizontal forces, I'll go normal to that. Let's see, sketch plane normal 2, there we go. Oh, there we go. I just right clicked. That's what I'm looking for. Okay, so these are fairly large loads in the tangential direction, but you can see them now at least. And, oh yeah, I wasn't actually in the sketch. There we go, I had the sketch highlighted. So you can see the magnitude of basically all the tangential loads in the tangential plane or the horizontal plane, from which I built a shear diagram, again taking things down by an order of magnitude so that it would all fit. And you can download this model. I've got it in Brightspace. You can download this and the spreadsheet I'm about to show you. But what's really interesting then is to see the moment diagram, and I meant to show it to you in the vertical direction. I didn't. I'll show you all of them in a second. So this is of course just the integration of the shear diagram. You can see where the moments peak, and this is just a graphical form of what you've already seen where we computed everything by hand. So if I were to, let's see, let's just turn on, what about if we turn on shear and moment diagrams so you can see them. There we go. And then we'll have a view What would look nice? Maybe something from here, something like that. I don't really like that. Let's rotate just a little bit so you can kind of see it. And of course you should download this model and play with it yourself too. But you can see how the shear diagram and the moment diagrams, well, there's two of them, right? There's one in the vertical plane and one in the horizontal plane, or essentially one in the radial and tangential plane is the way it worked out because of the way the gears are configured around the shaft. But these are very helpful diagrams because they help you see where the maximum loads occur, both moment and shear. So what I did then is I took all of those loads and I put them into a spreadsheet. So you can see the locations. You'll have to figure out, because I don't remember which it is right now, which side is which. Here's the larger torque load and the smaller, so that should help you orient the shaft. I don't remember which end I called 1 and which one I called 9, but I should have stuck with, I think they had A, B, C, D, and E. I should have stuck with that, but I didn't. Anyway, so from the shear and the moment diagram and the torque diagram, I put in all the moments, all the torques, and all of the shears. Now you'll notice I didn't put shear in the center. The reason for that is that I already know that the moment is highest in the center, and the moment is going to dominate the diameter requirement. You'll see that in just a minute. But I've got all of the loads along the length of the shaft listed here, and I highly recommend when you're working a shaft problem and designing it, you set it up this way. There is a computation method in, or I guess I should say module in M-Design, but it's not very good. I prefer to just do all this in Excel myself, and I think it's better that way. So in order to design these, remember that we have to switch over to my presentation. We have to get the moment and the torque, of course, which we've got now, and the shear. You see that in these equations to plug in. But we also need Sn prime. Okay, getting Sy is pretty easy. Once we choose a material, getting the yield strength is no problem. But how do we get Sn prime? Well, let me explain that in this example. We have to select a material, and so the one I selected, I chose AISI 4140 OQT 1000. So it's oil quenched and tempered at 1000 degrees Fahrenheit. And so I can look up the yield strength. That's easy. That's just in the back of the book. I don't remember the table now, but you should go and find it in your appendix and mark it. Now, how on earth did I get the what's called the modified endurance strength? Well, it's based on the ultimate strength. So I went ahead, and while I was there getting the yield strength, I read off the ultimate strength. And then what you can do is go into chapter 5, and in particular go to page 172. I've got a note about that here somewhere. There it is. There's a procedure on page 171, but 172 is where you need to be right now to see this particular diagram, the one in the upper left hand corner of the slides. And all you do is you just look up the ultimate strength or the tensile strength on the x-axis and go up to the particular curve that represents the way that the shaft you're designing is going to be made. Now, my assumption is that the shaft I'm designing is going to be machined. So it's going to be turned on a lathe. So what I need to do is go from whatever the tensile strength was. Let's see, what was that? The tensile strength was, let's see, 1, 2, 3, 4, 5, 6, 1.16 gigapascals. So I need to use that. Let's see, this is in KSI. I've got the wrong graph. I apologize. There's a metric graph on the same page, so you'll have to follow along there. But if you go over to 1.16 or so, then you'll see that the machined or cold drawn line has a really nice major diameter on the y-axis, or major division on the y-axis, and it goes up to 400 megapascals for, they call it either the endurance strength or the modified endurance strength on the y-axis. Sometimes you'll see me call Sn prime the modified endurance strength. That's wrong. The real term is the actual endurance strength. Okay, well, I mess up the names for things, so Sn and Sn prime are no exception. Anyway, so if you notice, I read off, and you should verify this in your book, it's also on page 171, I read off 400 megapascals as the modified endurance strength from that figure. And I got that by going on the x-axis here and going up to the machine curve and then going over to the modified endurance strength. Now, once you've got that, that's not quite enough, because look, we've got this whole equation we have to fill in. All we've got is this first term, Sn. There are a bunch of modifying factors we have to include as well before we get to Sn prime, which is what we can use in the equation. Now, the page 171 in your book is a page well worth marking, because anytime you're in Chapter 12 designing a shaft, I guarantee you're going to have to go back to this page. So mark it, because there's a really good procedure also on page 171. And the procedure says to specify the material for the part, determine ultimate strength considering its condition, how it will be used in service. Okay, fine. So I've done that, right? I've selected 4140. Specify the manufacturing process. I already did that. I said it's going to be not just wrought, it's going to be machined. And then use figure 5.8 to determine modified endurance strength. So that's step 3. We've already done that. We've got Sn. Step 4, apply material factor. So this is our first modifying factor, Cm. Now what it says is that you've got either wrought steel, cast steel, powdered steel, malleable cast iron, gray cast iron, or ductile cast iron. Well, most of the irons are going to be fairly brittle, and remember the procedure that we're using here in Chapter 12 is really only good for ductile materials. Now malleable cast iron is fairly ductile, and so is ductile cast iron. But most of the time we're going to be talking about either cast steel or wrought steel. So I'm going to assume that I'm making this, I think I assumed wrought steel as I recall. Cm, here's Sn prime. I didn't even note what I used. Yeah, I just assumed a value of 1, and that's pretty common. You may want to highlight Cm equal to 1, because that's usually the most reasonable selection for a shaft that's going to be expected to have relatively high strength. Now, if it's powdered steel instead, then you need to use 0.76 in the equation, but I'll leave that up to you. Step 5, apply a type of stress factor. So that's the subscript St. It's the next one in our equation here. So the type of stress factor, 1.0 for bending and 0.8 for axial tension. What is that talking about? Well, if the shaft has side loads on it, whether they are radial load or tangential loads, then it's tending to be bent, right? The moment is causing bending in the shaft. We're not so much worried about shear, although we do calculate for it. We're worried more about bending. That's typically what causes failure in a beam, or in this case, a shaft that is acting as a beam. Now, if you had a shaft where there was significant axial tension, where there was pulling on the shaft, then you would use a type of stress factor of 0.8. Again, most of the time we're going to have bending in the shaft, so we expect to have CST, the type of stress factor, equal to 1. So again, you should probably highlight that one because it's the one that you'll use most often. Now something a little more interesting. Apply a reliability factor. Well, if you flip over one page to page 173, table 5-2, I've got a small version of it here. You may be able to read it, maybe not. If half of the shafts that are made are acceptable to fail, then leave CR equal to 1. In other words, I guess if you're working for a very low-cost, cheap tool manufacturer, right, then CR equal to 1 is fine. Obviously, that's probably not what you want most of the time. So I chose a reliability, I think, of 0.999. Let me see what I used. Reliability factor, CR. I chose 0.75, yeah. So I chose a reliability, there it is, of 99.9%. Okay, so I'm assuming that if I make 1,000 of these shafts, one of them is going to end up failing because of this reliability factor. And then finally, the last thing is the size factor. Let's go back to the procedure. Apply size factor using figure 9.5 and table 5.3 as guides. Well, I've included those here for you. So there's table 5.3, and that is on, it's a couple of pages in. It's page 174. The thing about this, you can either use the equations in the table or you can use the figure. It's figure 5-9, as I said. And all you do is you go from the shaft diameter at that point up to the size factor. Now hopefully you just immediately thought, wait a second, we're trying to get Sn prime so we can get the diameter, right? So you're telling me to get Sn prime, I've got to already have the diameter to get CS? Yes, this is an iterative procedure. You have to guess a diameter, a size that seems reasonable, and use that. Now, here's what happens. CS is not all that sensitive to the diameter of the shaft. So unless you get to something that's very small on the left-hand side of the graph, then the size factor becomes more and more important. But as you move out on that curve, it sort of levels off a little bit. And so a lot of times what you'll just know, okay, I expect to get a shaft that's, I don't know, an inch in diameter or 10 inches in diameter or whatever. You expect a reasonable size given the loads. Now how do you know what's reasonable? You don't, not until you've had a little bit of experience. So what I usually do is I just assume a size of 3 inches. Just assume a 3-inch diameter. And part of the reason for that is there's a fairly close major division crossing. Sometimes I'll assume 1.5 inches just because that crossing is a little bit better. And I'll read off the size factor and put it into the equation. And then what I do is after I go through, I've got Sn prime, I use it in the equations for calculating diameter, then I go back and I double check that value of the size factor to make sure the diameters I've calculated are, reasonable, give me about the same value of CS. So I'll illustrate that for you. So I believe that I started off, let's see, yeah, based on about a 3-inch diameter shaft, I read off about 0.78. Now at this point, unless you're doing everything in a spreadsheet, I wouldn't bother using the equations in the table. I would just use the figure and read it off. But if you plan to set it up where everything's going to be in a spreadsheet, maybe you should bite the bullet and just go ahead and enter the equations from the table so that you don't have to read off of that curve. However you want to do it, you need an initial guesstimate for the size of the shaft. So I just guessed a 3-inch shaft, come out with about 0.78 for the size factor, and that allows me to calculate Sn prime, the actual endurance strength. So I've got 234 megapascals as the actual endurance strength. So now finally I can go into the equations for minimum diameter based on shear, that's this one, and minimum diameter based on the moment and torque, and I've got everything I need. Well, almost. I need a design factor in, and I chose a design factor of 4. I don't remember if your author recommends that somewhere in chapter 12. A lot of times he recommends 3. For whatever reason I chose 4. This is up to you as the designer. You get to choose what the design factor will be. And so then all I did is I noted all the different stress concentration factors, and notice I used 2.5 at the end. Remember, the end is where we've got a gear on the end. There was a snap ring groove, then there was a sled runner key set, and then a fairly sharp shoulder for putting the gear up against. Well, the sharp shoulder has a stress concentration factor of 2.5. At least that's what we're taking it to be in this class. Remember, that is a simplification. And the sled runner key seat has a stress concentration factor of 1.6. So we're not using that, right? Because 2.5 is greater than 1.6. So I chose the larger stress concentration factor for that section. And since I'm essentially out at the end of the shaft where there is no moment, then that's 0. There is torque in this section of the shaft because it's being transmitted through. And so I can calculate a minimum diameter based on the moment and torque. Let me show you what's in this equation. So this whole mess here, you see the 32, you see pi. And by the way, please don't use 3.14 in Excel. Use pi with the parentheses. It's easier to see where it came from and what it is. Anyway, so you see this 1/3 power here. That all came from, of course, this equation. You got the 32 here, the pi, the 1/3. We can see the features of the equation in Excel, and it matches if you double check it. Please do. You can get the spreadsheet. I've got it posted as well. But you can see where all this comes from, and you notice that I'm referencing the moment and the torque at that particular location in order to calculate a minimum diameter. Now the shear is there as well, so I can calculate a minimum diameter based on the shear equation. I'll show it to you. 2.94, there's a square root. That's the same thing as raising something to the half power. It's the same thing as square root. So you see the 2.94. You see the factor of safety in there right here, the purple B9 reference. And if you look at the equation in the slides, it's this equation right here. I'm using the right stress concentration factor, the actual endurance strength, and so forth. So there's the minimum diameter. Now, which one gives me a larger required minimum diameter? Well, since I'm out at the end of the shaft, it's the shear. Right? Notice the shear is giving me a larger required minimum diameter. And so I have to design based on this because it's bigger, right? This 0.028. What is 0.028? Well, these are in meters, and so since I want to specify in millimeters, then this is roughly 30 millimeters, and that's what I specified. Notice I did not use 28 millimeters. I went up to a preferred size of 30 millimeters. Okay. So then what? Well, as you move along the length of the shaft, the stress concentration factor that's appropriate changes, And of course this section, if you're wondering where it's at, I'll show you in the shaft. Really the first one, I don't remember which end it would be on. That doesn't matter too much. But the first section would essentially be here. Okay, it would be at the shoulder. The next stress concentration factor is going to be right about here. So I'm using this one next, and that's why I'm using a stress concentration factor of 1.5. Now, in reality, the moment is a little different than what I've put in here, but I'm just putting in the maximum moment in the general area in order to increase my factor of safety. Now, I really probably should decrease this safety factor because I am putting in the worst load I can find in the general area. And so this is going to be a very conservative design. Is that good? Is that bad? Well, it depends on the application, right? I mean, if this is a piece of equipment that sits on the ground and who cares how much weight there is and it's got plenty of space, then what difference does it make? I repair electronics sometimes as a hobby, and sometimes I'll find these fairly exotic capacitors, fairly expensive capacitors that designers have used, and they're really small, and they're supposed to be very high performance capacitors, and they go out. And the funny thing is that there's plenty of headroom. They could have chosen a much taller capacitor. They could have chosen a larger diameter capacitor, and it would have been cheaper and been more reliable, because generally as capacitors get smaller, they get less reliable. Manufacturers try to pack as much into them as possible. And so always choosing the highest performance part, or the highest performance material by analogy here, isn't necessarily what you want to do. That just adds cost when it's unnecessary. So I have chosen a fairly strong material, and again, this is a fairly conservative design, but there's some room for change if necessary. So as we move along, we're going all the way to a sharp shoulder again here, and then finally the snap ring groove going towards that middle gear. You can see the moment torque prediction of required diameter increasing as we go, and you notice that very quickly the shear equation gives you, what, a half or so of what the moment torque equation is predicting is the minimum required diameter. So by the time I got to the center of the shaft, I saw this and I thought, why am I continuing with this? There's no need. I didn't even bother typing in the rest of the shear numbers because I know that the shear is not highest in the center of the shaft, so there's no point in even considering it. It's the moment that's going to cause the damage. So I just considered with the moment equation and minimum diameter based on the moment. So I do recommend you download this spreadsheet, look through it, look through the model quite a bit, and try to understand everything that I've done if there's something you're confused about. Some interesting notes. I've got 30 millimeters here, 60 millimeters, and then 65. What are those? Well, I think I updated my model so that those would reflect these designs. So 30, 60, 65. Yeah, so this should be the 30 millimeter diameter section. Let me evaluate and measure that quickly. Nope, I did not update it. I've got this as 50 millimeters, so that's larger. Anyway, the idea was that this section would need to be at least 30 millimeters. The next section is the 60, and then this is the 65 millimeter diameter for the sake of the bearing. So I chose a bearing that would have a 65 millimeter bore. Sorry, the model doesn't match the calculations exactly. But then I used a 69 millimeter diameter, and you might look at that and say, well, wait a second. That doesn't seem right because that's not a preferred size. Why on earth would you do that? Well, I'll show you. That diameter is right here. Now, does it really make sense to turn down a whole lot of material on the shaft and spend a lot of time in machining, reducing this shoulder, so that, remember, I've only got about a 4 millimeter shoulder here, right? And that's the diameter difference, so that's going to be spread across two. So that's only 2 millimeters of meat there to keep the bearing from sliding any farther down the shaft. Now, I do want this section smaller than this section because the gear needs to have a bore that matches this section nicely, so that when I put the key in and clamp it in place, hopefully it won't have any play on the shaft. That's the idea. But I don't want to have to pound it over this section, so giving it a millimeter of clearance is a fairly generous thing, so that then it can go on over here and be assembled easily. So the reason I chose a 69 millimeter diameter here is, number one, save machining time. I could have said 69.5 millimeters if I really wanted to, but why not take off a full millimeter while we're at it? And hopefully machinists would see this unless they're used to it, or maybe I've put a note on the print that this surface could be a fairly rough surface. I'm just trying to get material off of it to make it easy to assemble the center gear. Now I don't want it too rough because I don't want stress concentration factors that are above, but I've already got a snap ring groove here, so that's going to be the major stress concentrator. Again, I'm just going along the entire shaft. We've got a 70 millimeter diameter, a preferred size for the center gear, another 65 millimeter bearing, and then finally the gear on the end is 30 millimeters as well. And so you notice that the shaft ends up being symmetrical, and I really prefer to design that way if possible, because if it's something where the loads are, okay, the moment's higher on one side of the shaft than the other, the torque's higher on one side than the other, but you notice the diameters don't really come out that much difference. We got 55 millimeters here and 50 millimeters here roughly. That's not that much material, right? And if I'm going up to 60 millimeters on one side anyway, I may as well make this shaft where it can be inserted either direction if that's possible. And that way, assembly is simplified and easier, and it's not like I've got a 1 millimeter difference that's hard to see and difficult to tell which way you should put the shaft in. No, it's just symmetrical. So that's the way I designed it. Now, what if these were just too large? What if I said, I just don't have room for that large a diameter of shaft and the resulting bearings and gears and things? Well, then I could go to a stronger material. Now, it may be a little difficult to find something stronger than 4140, but there are some out there. What if, on the other hand, I look at this and I say, that's a fairly small shaft, I've got plenty of room, and this material is fairly expensive? Well, I could just change the material, right? All I got to do is change the ultimate strength, get the modified endurance strength, and then calculate the actual endurance strength. And if it's a weaker material, I will ultimately end up with larger required diameters here. Okay, and if that's what happens, fine. I have the space for the shaft. So you can play with things. You can move the material around. Now, understand you won't change the stiffness of it. You won't really change the resonant frequency of the shaft, but you can change the overall size. Obviously, the weaker the material, the larger the diameter of the shaft that's going to be required. Another thing to finally circle back on is this size factor. Remember, I estimated about a 3-inch shaft or so. And I think that figure has metric on it as well, metric dimensions. Yeah, the secondary x-axis down at the bottom has diameters in millimeters. The largest diameter I've got is about 70 millimeters, and that ends up being just below 3 inches or so. The smallest diameter I've got is 30 millimeters. Now, the way you use the size factor, as the diameter goes up, the size factor goes down. In other words, the material becomes weaker. And so what I usually do, I don't bother trying to calculate a different SN prime for every single row. You could do that if you wanted to, but the difference is not all that great. What I usually do is I go through the procedure once, I look to see what the largest diameter is, and base my size factor on the largest diameter. And is that right? Is it wrong? Well, remember that in what we're doing in this class, we're not looking for one right answer. We're looking for an answer that works. We're designing, and there are many different solutions that are possible, that are valid, that work. And the more you refine a design, the more sensitive that design becomes to changes. Notice I've got a nice big safety factor here of 4. I've used the largest moments. So if somebody accidentally uses a material, or we get in a bad batch of material that's not quite as strong and somehow it slips through and the shafts are made, they're probably going to work anyway. And I think that little bit of cushion is worthwhile. So everywhere you see I've kind of chosen a conservative route. Now, if this is in an airplane or a helicopter or something that has to fly, this may not be good enough. I may have to refine the design further, and I'm sure there'd be all kinds of other regulations and rules and design rules of thumb and things that I would have to include that I don't even know about at this point. But this should be a valid design. It's a good starting point, and since it's set up in a spreadsheet, I can modify it and change it and refine it as far as I want.